Hi, today we continue our discussion on reflection of plane waves under normal incidence condition, and we talk about design of matching layers. Last lecture we saw that by putting a lambda by 4 coating it is possible to remove reflection from a particular frequency. So the thickness of the coating is quarter wavelength at that frequency. This will give certain bandwidth, that is, reflection coefficient, for example, will be less than certain specified number, so specified value over a band of frequencies. So if you see, there are two figures here. The left figure the figure on the left we are familiar with. This is gamma in or tau and tau out as a function of frequency. So the design frequency was chosen to be 6 10 to the power of 14 hertz, and therefore the reflection coefficient there is very low. And the figure on the right is very similar one, but the scale has been modified a little bit. Instead of plotting the frequency, we have plotted normalized frequency, that is frequency upon f naught, the design frequency. In this case, f naught happens to be 6 10 to the power of 14. Therefore, at f upon f naught, the reflection coefficient will be 0. And the other change we have done is the gamma in scale on the left side, on the left figure, was in decibels. We have converted them into linear scale. This is little convenient because I want to show something about the nature of reflection coefficient when it is very close to 0. And for that, it is best shown in a linear scale. Hence, I have modified this into a linear scale. Otherwise, it's exactly the same figure. So what is that we observe here? This has single resonance, that is, it's got the best performance at a single frequency, and it has certain finite bandwidth. That means if I say that the performance should be better than certain reflection coefficient, whatever be that certain number, then that can happen over a band of frequencies only. So the question that we ask is it possible to increase that band of frequencies? What is that we can do to make this matching system broader in bandwidth? That means it matches over wider range of frequencies, and the choice should be with me. And how much it reflects back, if I can control it, all the more better. We are going to answer some of these questions in today's lecture. We'll go back to our small reflection theory. We had a dielectric slab, and the reflection coefficient at the front surface was gamma 1. Reflection coefficient at the second surface or the back surface is gamma 3, where gamma 1 is eta 1 minus, eta 2 minus eta 1 upon eta 2 plus eta 1. Gamma 3 was eta 3 minus eta 2 upon eta 3 plus eta 2, according to this figure. Okay, and gamma in was given by the equation on the left. Suppose the magnitude of gamma 1 and magnitude of gamma 3 are very small compared to 1, gamma 1 times gamma 3 magnitude will be very small. Therefore, we can approximate gamma in as gamma 1 plus gamma 3 times e to the power of minus j 2 beta 2 d. We are making the denominator equal to 1. This is known as small reflection approximation. So this is a very convenient approximation to build a system which has multiple such layers. Now let's consider that. Consider multiple layers here. We have a medium from which some light is falling, which is supposed to be, in this case, we have taken it as free space with epsilon naught mu naught having an intrinsic impedance eta naught and a propagation constant beta naught. It falls on multiple layers. Layers 1, 2, 3, 4, etc. up to capital N. Each has epsilon mu of respective values, epsilon 1 mu 1, epsilon 2 mu 2, etc. and intrinsic impedances eta 1, eta 2, eta 3, etc. up to eta n. And then there is another bulk layer which is labeled as L, which is epsilon L mu L, corresponding intrinsic impedance of eta L. This could be glass. The first incident region is free space. Now we are designing a matching layers here, matching system here, such that the reflection seen at the input, which is gamma in, is very small over a broad band of frequencies. The question we are going to be asking is, how do we do that? So for to do that, we have to develop a theory. So we are going to develop a theory for multi-layer reflection system. So let us take the first one here, the first layer. The incident, we have to find out gamma in, and imagine that there is only one slab, slab number 1 of thickness d1. The reflection coefficient at the first interface is gamma naught. At the second interface, it is gamma in 1. Gamma in 1 is the reflection coefficient in the presence of all the remaining layers and the layer number L as well. So by using the small reflection approximation, you can write gamma in as gamma naught plus gamma in 1 e to the power of minus j 2 beta 1 d1, where gamma naught is eta 1 minus eta naught upon eta 1 plus eta naught. Convinced? Good. Now we develop it further. What do we do? We go into the second layer. We remember the equation for gamma in. Now we ask the question, what is gamma in 1? Gamma in 1 was the reflection at the interface between layer 1 and 2, which takes into account all the layers to the right of the interface. Now, therefore, gamma in 1 using small reflection theory can be written as gamma 1, that is the reflection coefficient at that interface, which is eta 2 minus eta 1 upon eta 2 plus eta 1, plus gamma in 2 times e to the power of minus j 2 beta 2 d2. What is gamma in 2? Correct. It is a reflection at that interface between layer 2 and 3, taking all other layers into consideration. Can we write gamma into similarly? Yes, we can write gamma into similarly, but before that, we'll substitute gamma in 1 in the previous equation and expand it. Convince yourself that this expansion is indeed correct. Now, we do the same thing for the interface between second and third layer, where gamma in 2 in overall in reflection coefficient is that gamma 2 plus gamma in 3 times e to the power of minus j 2 beta 3 d3. Substitute in the previous equation for gamma in, and the expression is started growing now. Can we do this for all the layers up to layer number n? Yes, we can do it. It's a simple, addition. Keep adding all the terms. And I'm interested in the nth term, which is, or n plus 1th term in this case, because first term is gamma naught, which is gamma n e to the power of minus j2 summation n equal to 1 to n beta n dn. This is very straightforward. It's just an extension of generalization of each of those terms there. For the first term, it was beta 1 d1. Second term was beta 1 d1 plus beta 2 d2. For third term, it is beta 1 d1 plus beta 2 d2 plus beta 3 d3, and so on. Nth term will have n summations, beta n dn summation n equal to 1 to n. Correct? Good. Now we have a nice, beautiful, long equation. We'll worry about it. We'll make it, simpler in a moment. Now we make one approximate assumption. Each slab, we assume that it is quarter wave thick at a particular design frequency. We'll come to that. So that is beta n dn is equal to 2 pi by lambda n, because beta is 2 pi by lambda, and dn is quarter wave thick, that is lambda n naught by 4. What is lambda n naught? Lambda n naught is related to velocity and f naught via the relationship Vn equal to f naught lambda n naught, where f naught is the design frequency and lambda n naught is the wavelength in that small nth medium at the design frequency f naught. Therefore, dn will be lambda n naught by 4, and Vn is f naught lambda n naught. Vn is also equal to f times lambda, because the velocity in that nth medium is Vn always. If you change the frequency, the corresponding wavelength will change. And if you substitute these two, we can say that beta and dn is equal to pi by 2 f upon f naught. Let us give a small symbol called theta. Theta is related to f via this relationship pi by 2 f by f naught. We keep coming back to this relationship very often in this lecture, so let's remember it. If you want, note it down somewhere. Now, gamma in now gets simplified, which is gamma naught plus gamma 1 e to the power of minus j2 theta plus gamma 2 e to the power of minus j4 theta, and so on, gamma n capital N e to the power of minus j2 capital N theta. What is gamma small n? It is eta n plus 1 minus eta n upon eta n plus 1 plus eta n. This is the reflection coefficient at which place? between layer n and layer n plus 1. Yes, that's gamma small n. So the convention I'll be using is, when I write gamma n, it is the reflection coefficient at the layer n. If I write gamma in, it is the overall reflection at the input of the system. So this is our summary. We have gamma in, which can be in a compact format written as summation n equal to 0 to capital N gamma small n e to the power of minus j 2 small n theta, which can be expanded, of course, and theta is given by pi by 2 f by f naught, and gamma n itself is given by that equation which we are familiar with. Now if you see this gamma n, it is basically a polynomial. It's a polynomial of degree n. Therefore, it has n zeros. We can choose the zero location. Basically, if I choose gamma naught, gamma 1, gamma 2, all these values appropriately, the zero location is frozen. If I change the values of gamma naught, gamma 1, etc., the zero locations will change. So instead of worrying about what gammas I should be choosing, I will now start reverse engineering. I will say, can I choose the zero locations? If I fix the zero location, I can always compute gammas and then compute eta n straight away from the other result there. Very good. So we now make a particular choice. Gamma n, which is equal to n equal to 0 to n, gamma n e to the power of minus j 2n theta. We write this equal to some complex quantity a times 1 plus e to the power of minus j2 theta whole to the power of n. What have I done? We have chosen all the zeros to be at the same location. We have made a choice. So we can take out e to the power of minus j theta outside. So it becomes e to the power of minus j capital N theta, because the whole thing is to the power of n, and you are left with e to the power of j theta plus e to the power of minus j theta. And this is nothing but 2 times cosine theta. Yeah, that's straightforward. That is 2 to the power of n cos theta to the power of n. Now this is gamma in, and we want to find out a. We know that this gamma in is equal to the gamma in on that summation also. Yeah, let's remember that. Now let's also ask the question, what happens when f goes to 0? When f goes to 0, theta goes to 0, and still this result is valid. Correct? Now there is an interesting observation. What is the meaning of theta going to 0? Theta going to 0 implies beta 2 d2 is going to 0. That means that slab doesn't exist. Nothing exists there. Everything is shrunk. That means gamma in is a to the power of a times 2 to the power of n is eta L minus eta naught upon eta L plus eta naught. Can you visualize this? We had so many slabs. We have shrunk all the slabs and we have nothing there. What we have is medium 0 having an intrinsic impedance of eta naught and medium L having an intrinsic impedance of eta L. And the reflection coefficient is gamma n. Therefore, gamma n is given by this result, which is equal to a to the power of n, because theta is equal to 0. Now we know what is the value of a. That's very straightforward now. Now we can substitute back in this equation. Therefore, gamma n can be written in this format here. Please verify that to convince yourself that I have not made any clerical or numerical errors, or some mistakes haven't crept in. This is a useful result. We'll be using this to see how to synthesize the system. Now, if you see the top equation, that's the same result that we saw earlier. We have just now proved that. Now, if you see the second part of the top equation, last part of the top equation, this is can be expressed in the form of a binomial series, and which is nothing but n equal to 0 to n, capital N C small n e to the power of minus j 2 n theta, where n c n is n factorial upon n minus n factorial times small n factorial. Please verify some of these results. If you have forgotten, it's always good to go back and make sure you remember these results. These would be useful to you, especially when you are solving an assignment or taking an examination. These results would be useful. And now we have gamma in therefore is, oh, we also know that gamma in is equal to n equal to 0 to capital N, gamma n e to the power of minus j 2n theta. We have two results. One for gamma in given or expressed in terms of gamma n's, gamma small n's. Another one gamma in expressed in terms of eta L, eta naught and ncn. These two should be the same, because we want that this polynomial, which was assumed to be 1 plus e to the power of minus j 2 theta to the power of n, should represent our reflections of the, that is gamma in, that is generated by our system of multiple slabs. Therefore, these two gamma ins must be same. So we just have to match the coefficients to get the value of gamma in. That is not a very complicated job. If we match the coefficient, it's very easy to write that gamma n is equal to 2 to the power of minus n, eta L minus eta naught upon eta L plus eta naught, n c n, that is capital N C small n. So we managed to find out gamma n, that is given eta L, given eta naught, given capital N, we know the value of gamma n for each of those n ranging from 1 to capital N. Okay, we are ready to now specify the performance metric, which is the reflection coefficient, the maximum value of the reflection coefficient that the system can tolerate over a specified bandwidth. Suppose gamma n is the reflection coefficient at f equal to fm, and delta f happens to be the bandwidth, then delta f is equal to f naught minus fm multiplied by 2. Therefore, we can specify fractional bandwidth as delta f by f naught, which is 2 times f naught minus fm upon f naught, or 2 times 1 minus fm by f naught. Do we know what theta is? Theta equal to pi by 2 f upon f naught. If I make theta as theta m, f becomes fm. Now I have a relationship between theta m and fm by f naught. Therefore, I can express fm by f naught as 2 theta m upon pi. Substitute back in this equation, we have delta f by f naught as 2 times 1 minus 2 theta m upon pi. So given the value of delta f by f naught, I can calculate the value of theta m. Very useful result. Gamma m is specified, so we will remember that. And of course, theta m, given delta f by f naught, we can also calculate theta by switching the things around. That's no big deal. Now, what is gamma in? If you remember this equation, it is given as eta L minus eta naught upon eta L plus eta naught e to the power of minus j capital N theta cos theta to the power of n. Go back few slides, you will see how we got this result. And mod gamma m, that is when theta equal to theta m, gamma n is equal to mod gamma m. Therefore, mod gamma m is mod of this quantity, and theta m itself is given by pi by 2 1 minus delta f by 2 f naught. So if I know mod gamma m, I can calculate theta m. If I know theta m, I can calculate delta f by f naught, the fractional bandwidth. If I know fractional bandwidth, that is delta f by f naught, I can calculate theta m, and I can also calculate the value of mod gamma m. So mod gamma m can be written in terms of delta f by f naught. So they are not independent of each other. Given the value of eta L, eta naught, and the value of number of layers capital N, then what you can achieve, what bandwidth you can achieve for a given value of gamma m, or what gamma m you can achieve for a given value of bandwidth is fixed. So we don't have control on two independent variables here. If you specify gamma m, delta f by f naught is fixed. If you specify delta f by f naught, the maximum value of gamma m is fixed. This will be our design constraint. We are going to be playing around with capital N to satisfy the conditions of both delta f by f naught and gamma m simultaneously. Confusing? I believe. So next example will make it, what I'm trying to say, probably a little clearer. Let's do that. Before we go there, we'll also write theta m as this result is for completeness sake. and delta f by f naught as this one from the left equation, and therefore you can also write delta f by f naught in terms of gamma m. These two are useful in the sense that if delta f by f naught is specified, use the left equation to compute gamma m. If let me point it out. If delta f by f naught is specified, use this equation to compute gamma m. If gamma m is specified, use this equation to compute delta f by f naught. Now, let's talk about design procedure. What is given to us? Eta naught, that is the impedance of the medium from which the wave is incident, onto a medium whose intrinsic impedance is eta L. And we also want to achieve a maximum value of gamma m over a bandwidth of or fractional bandwidth of delta f upon f naught. So these values, these four numbers are specified. Given these four numbers, we choose n. Magic, you choose some number, it doesn't matter what it is, an integer. Now, select either delta f by f naught or gamma m and calculate the other one. So we know these equations. You pick any one, calculate the other, and you convince that the system is met, specification is met or not. If the spec is met, brilliant, reduce the n and you can cross check. If the spec is not met, you modify n. When you say it is not met, when you say modify, you are supposed to increase the value of n. So if you increase the value of n and keep doing it until the spec is met. Once it is met, you can calculate gamma n using that result, which is coming from one of the previous slides, and you calculate eta n, and hence you can calculate epsilon rn, beta n, lambda n, dn, everything is specified, and you calculate the value of gamma in, the total internal input reflection coefficient. That completes the design. That is, given the two intrinsic impedances of the medium and the incident medium, given the value of maximum acceptable reflection coefficient gamma m over a fractional bandwidth of delta f by f naught, what have we done? Our design has been to decide the value of capital N. That's all we have done here. By going in loops, in circles, we have identified the optimum value of n. That is, in this particular case, the smallest value of n that will satisfy all these conditions. And once we know the value of n, we just have computed the characteristics of the n layers as well as the overall reflection coefficient. Let's show this with an example. Suppose eta naught is 376.73 ohm, that is the impedance of free space, and the other end happens to be a material with a permittivity of 2.25. Therefore, eta L is 376.73 upon square root of 2.25, whatever be that number, MATLAB handles it. Maximum allowed gamma m is 0.01 or minus 40 dB. Delta f by f naught, I would want 0.8. That's my requirement. If I choose n equal to 1 and delta f by f naught 0.8 implies I am looking at f by f naught of 0.6 and I want to see whether I have achieved 0.01 or not. Convince yourself it is indeed 0.6. If not, I'll answer this. I'll explain to you in the class when we meet on Monday. Probably not this Monday, next Monday. Right. So therefore gamma m we get as 0.11756. Sorry, 1176. It doesn't meet the specification of 0.01. What do we do? Increase the value of n equal to 3, we get 0.041. N equal to 4, 0.024. Hey, are you watching something? The shape of the curve is changing. It was very sharp. It became shallower, flatter, flatter. N equal to 5, it's really flat. And we achieve 0.014, still hasn't met the spec. N equal, right. Now we'll choose n equal to 6. And we get gamma in as 0.008247. I ignore the decimal places. No, those many significant figures. Happy with 008. It meets the specification. What is very interesting in this design is over the delta f by f naught, the reflection coefficient has a behavior known as maximally flat. That means the worst value of reflection coefficient happens at the band edge. And inside the band, everywhere, the reflection coefficient is always better than the value that is found at the edge of the band. This is number one. Number two, as we increase the order of the matching network, this curve becomes flatter and flatter. And that is how you are able to achieve broader bandwidth, wider bandwidth for a given value of gamma m.